Hello everybody, in this video I'm going to show you how to do water potential calculations. Now for all of the calculations that you will do in AP Bio, you will have the equations to do these calculations, but of course you need to understand how to use them. So the first equation is the equation for water potential, and it is this Greek symbol psi is the water potential symbol. So water potential is equal to the pressure potential plus the solute potential for a given cell, typically, which is what we're talking about. And just to give you an example here of exactly how this works, you have, for a given plant cell, so green for plant, you have a cell wall, and the cell wall is, fairly strong. And right on the inside of the cell wall, you have your cell membrane, and the cell membrane is fluid. It's able to move. And on the inside of your actual, cell right here, you have, dissolved stuff, sugars and ions and things like that. So there's actually a concentration of stuff inside here. That is going to be your solute potential, okay? And we can calculate that solute potential, and I'll tell you how to do that in just a second. And then if this particular cell here was, say it was in a beaker, and inside that beaker there was, some water, okay? So just pure water. The water's tendency is going to be to move from outside to inside the cell because there's more stuff dissolved in here than there is out here. So water is going to move via osmosis inside here. So you'll have water movement going into the cell. Now, as the water moves into the cell, so water moving in, you're going to start to have the cell fill up, and the pressure of that water is going to start to push, up against the cell wall here. The membrane will bump up against the cell wall, and it's going to push back on the cell wall, or up against the cell wall. And what that is going to do is it's going to create your pressure potential with the actual cell wall kind of pushing back onto the water and solution inside the cell. Now this pushing back is your pressure potential, okay? And this is not something that is easy. I mean, it's easy to calculate, but you can't really measure it inside of a cell. But you can figure it out if you have access to the water potential and the solute potential. So let's talk about the solute potential. So solute potential. This is equal to the negative ionization constant, so negative I, C, R, T. Now, what do each of these things mean, okay? I is equal to the ionization constant. Ionization constant, okay? And the ionization constant is just how many ions does whatever the stuff that's dissolved in the water make when it's in water. Usually for biology it's 1 or 2 because we're dealing with things like sucrose, which stays as one molecule in water, or something like salt, which when it goes into water it forms 2 ions. So for salt it would be 2, but that's what I is, okay? So the negative ionization constant. C is the concentration in molarity, so moles per liter. Okay. R is equal to a constant, which is 0.0831, and it's bar liters per mole Kelvin. Kelvin. And that is the unit for the constant for our equation here. You do not need to memorize this. All of this information is going to be given to you on your equations sheet, just so you remember. And then T is temperature in Kelvin. And to get Kelvin, remember, you just take your Celsius temperature and you add, so Kelvin is, it's Celsius plus 273, and that gives you Kelvin, okay? So it'll convert any Celsius to Kelvin by just adding 273. Okay, let's solve this problem. Now, recall that water potential is equal to pressure potential plus solute potential, okay? Now, I'm going to you can pause this if you would like to try to solve this on your own. If not, I'm going to work through the problem. All right, the first thing that we need to do for this problem is we need to solve for solute potential. Okay, so we know, I'm just going to put this right up here, we know that solute potential is equal to the negative ionization constant times CRT. Okay, let's solve. Solute potential is equal to -1 times the concentration in molarity, which we know to be 0.5, which is in moles per liter. Okay, the ionization constant is 0.0831 bar liter mole Kelvin. Okay, and then degrees in Kelvin, so temperature in Kelvin. So 20 degrees plus 273 is equal to 293 Kelvin. Ran out of room. Okay, there we go. Now, let's just see what this does to the units. Okay, liters is going to cancel out here and here. Moles is going to cancel out here and here. And Kelvin will cancel out here and here. So what we're left with is a unit of bars. Okay, so the solute potential is equal to, okay, so the solute potential is equal to -12.17 bars. All right, now, if we wanted to solve for water potential, you could solve for water potential, which is equal to the pressure potential, which we know from right up here. Oops, sorry, I shouldn't delete that. Pressure potential is right up here, so we could enter in water potential is equal to pressure potential, which is 5 bars, plus -12.17 bars. Okay, and our answer is going to be -7.17 bars. Okay, so -7.17 bars. Sorry, ran out of room. Okay, so water potential is equal to pressure potential plus solute potential. You'll be given the information that you need up here, and you can go from any point from this equation here. As long as you have one part of the equation, you can find the other parts of the equation. Okay, now most often what will end up happening is you'll get a question where you're asked, what direction is the water going to move? And they'll give you, or you'll have to calculate some part of that problem, okay? Now, in this super high-tech drawing, okay, we have a beaker here and a cell, okay? I'm going to give you the water potential of the inside of the cell. And remember, for the cell, the water potential equals the pressure potential plus the solute potential. So I'm just going to give you the cell's water potential. Let's say the cell's water potential is -3 bars. Okay, sorry, ran out of room. All right, now, what I want you to do is I want you to tell me in this equation, or in this problem, what direction is the water going to move? Now, water always moves from an area of high water potential to an area of low water potential, okay? So that is the direction that it's always going to move, okay? So from high water potential to low water potential. Now, in this problem here, I've given you the water potential inside the cell, and I'm going to ask you to calculate the water potential for the solution in the beaker. Now remember, the water potential of the solution in the beaker in an open container is just equal to the solute potential. There's no pressure acting on on the top of this water, okay? Because apparently we're doing this on a mountain, okay? So we're just, pressure potential is going to be 0, and it's negligible, okay? So we're just, the solution itself, the solute potential, water potential for the solution here is going to be the solute potential. Now, let's assume that the temperature for our beaker, okay, so the temperature is 20 degrees, okay, Celsius, and that the molarity inside here is 5 molars, so moles per liter, okay, so whatever the solution in here, and let's say it's sucrose, okay, so we also know sucrose has a ionization constant of 1. Okay, so let's calculate this water potential for the solution in the beaker, and let's see which direction the water is going to move. You can pause this if you'd like to calculate it on your own. Otherwise, I'm going to go ahead and do it right now. Okay, so we need to figure out the solute potential, and we know that that's the negative ionization constant times CRT, okay? So our ionization constant is 1 for sucrose, so -1, times the concentration, which is 5 mole per liter, times our R, which is 0.0831 bar, liter, mole, Kelvin, okay? And then our temperature, which is going to be 293 Kelvin. When I calculate this, I get that the solute potential is equal to -121.74 bars. That's high. Just random numbers, but that is very, very high, or very, very low, sorry. So -121.74 bars. Now, we need to figure out what direction the water is going to move. Water always wants to move from an area of high water potential to low water potential. And right here, inside of our cell, our water potential was -3 bars. Outside, in this solution, we calculated that the water potential, which is equal to the solute potential, is -121.74 bars. So water is most definitely going to move from the cell, out. So it's going to move, it's a very large arrow, it's going to move from the cell out into the actual beaker. Because, as we know, -3 is definitely greater than -121.74 for sure. So that's how you calculate water potential. I hope this was helpful, and I'll see you guys soon.